Most recently, we've been talking about series, and now we want to go back to our earlier topic of sequences. And one of the basic things when you're studying anything in mathematics is to look at the sub-objects of the same type. So for example, in vector spaces, you have subspaces. In rings, you have subrings. Like in the real numbers, you have the rationals or the integers and so on. So in the context of sequences, you have subsequences. Given a sequence A1, A2, A3, ... What we mean by a subsequence is we pick out just certain indices from the original sequence of integers that index the original series. We pick out a sequence of positive integers, n1, n2, n3, ... And we use these as indices to pick out a subsequence from our original sequence. Then our subsequence will look like this: a n1, a n2, a n3, ... Certain properties of sequences are going to be inherited by their subsequences. So for example, consider a subsequence ank of a sequence an. Now, if the original sequence is bounded, then the subsequence is also bounded by the same bound, which will also work for the subsequence. This is obvious. If a sequence converges, then each of its subsequences also has to converge. Well, to the same limit, in fact. And this should also be obvious. If a sequence is increasing, then so is any subsequence. Or the same thing for decreasing, or monotone in place of increasing. Next, observe that subsequences of subsequences of an are still just subsequences of an. You just have to think about these statements and convince yourself that they're true for obvious reasons. But something this obvious can still be pretty useful. For example, consider the sequence of real numbers whose nth term is sine n. So there's a sequence of numbers between -1 and 1, and it appears to go all over the place between -1 and 1. There's a graph that I can show you here, which shows you something about what that sequence is like. The vertical heights on these white bars are the terms of the sequence. The sequence is clearly bounded. All its terms are between -1 and 1. But if I didn't show you this picture, if I just listed decimal values of the sequence, you wouldn't even see probably this much. They would just look like more or less random numbers between -1 and 1. And it wouldn't be clear what's happening. We want to show that this sequence diverges. And an easy way to show this, maybe the easiest way, is to use subsequences. We can find a subsequence shown in blue whose terms are all greater than or equal to a half. And you can find another subsequence shown in green whose terms are less than or equal to minus a half. And this will give us what we want. As you'll see, first of all, to get the blue subsequence, for each positive integer k, you look at the interval from 2k pi plus pi over 6 to 2k pi plus 5 pi over 6. This interval has length 2 pi over 3. That's an interval bigger than 1 in length. Well, there's got to be an integer in that. If you take an interval on the real line of length more than 1, it's got to contain at least one integer. So let's pick an integer in this interval, call it mk. The interval we chose is because of what we know about the sine function. The sine function is greater than or equal to a half on that interval. So let's just simply take mk to be the smallest integer in that interval. If there's two of them, then just take the smaller one. That'll avoid the axiom of choice. So let's just say that mk is the smallest integer in this interval. And similarly, choose an integer nk in the interval from 2k pi plus 7 pi over 6 to 2k pi plus 11 pi over 6. Once again, this interval has length 2 pi over 3, bigger than 1. So there's going to be at least one integer in that interval. Let nk be the smallest integer in that interval. And once again, by our choice of intervals, this subsequence in green is going to have terms less than or equal to minus a half. Again, just by basic trigonometry. Now, our argument will use contradiction. So if our sequence sine n converge to L, then every subsequence must also converge to L. In particular, the subsequence in blue would converge to L. But these terms are bounded below by a half, so the limit L would have to be greater than or equal to a half. This is one of the properties that we used about limits that involve the order relation. But also, the green subsequence has terms less than or equal to minus a half. So for it to converge to the same limit L, L would have to be less than or equal to minus a half. And there's a contradiction. So here we have a great way to prove divergence. Find two subsequences that are far enough apart that they cannot possibly have the same limit. Now, the rest of this video is devoted to a major result. It's known as the Bolzano-Weierstrass Theorem. We're packing a lot into our PowerPoint slides, kind of pushing the limit of what fits on a slide. So I'm sorry for that, and you'll be tired of looking at it. But let's have a go. You know that every convergent sequence is bounded, and the converse is definitely not true. We have counterexamples of bounded sequences that do not converge. But every bounded sequence of real numbers has a convergent subsequence. And again, this is using the completeness of the real number system. Let's prove this result. We start by giving a sequence of real numbers, an, that's bounded. Somebody gives it to us. It's in the interval from minus m to m. We need to show that this has a convergent subsequence. Our strategy will be to use the nested interval theorem. So we can find a chain of closed subintervals getting smaller and smaller, each containing infinitely many terms of the sequence. And by the nested interval theorem, there will be a point in their intersection. And there will in fact be only one such point if we choose our intervals to get small fast enough. So by our construction, we'll recover a subsequence converging to a point. That'll give us a convergent subsequence. That's at least the idea. So what is this sequence of closed subintervals? Well, the first subinterval is the entire interval minus m to m. I'll call that interval I1. It contains the entire sequence, so that's a good start. Now the remaining subintervals in my chain will be constructed recursively. We're going to bisect each interval into left half and right half. And when I do that, either the left half or the right half will have to contain infinitely many points of our sequence. Maybe both of them, but at least one of them. If you have an infinite number of points in an interval, you chop the interval in two. Either the left half has an infinite number of points of the sequence, or the right half has an infinite number of points of the sequence, or maybe both. So we choose that one for our next subinterval in our chain, and recursively that gives us the chain of closed subintervals. So each of these intervals is exactly half as long as the previous subinterval. So that tells you the length of each subinterval is a power of 2 times m. And by the way, you can check when k is 1, that's 2m is the total length of the interval. And every time you increase k by 1, then you're dividing the length of the subinterval by 2. So that more or less tells you this formula for the length of each of our subintervals. And if you want, you can formalize this argument as a proof by induction. The important thing here, however, is that our intervals are getting small. The length of the kth subinterval goes to 0 as k goes to infinity. Now, where's our subsequence coming from? Well, we recursively construct a subsequence, ANK, of the original sequence such that the kth term of our subsequence, ANK, is in the kth subinterval. How do we choose that? Well, we take n1 equals 1, so A1 is in our I1 subinterval. That's a good start. And next, for each successive value of k, for k at least 2, let nk be the smallest integer greater than the previous index, nk minus 1, such that ank is in I sub k. And we know that we can choose that. Why? Because there are infinitely many terms of our sequence in ik. By the way, we chose our sequence of closed subintervals. And you just go far enough out in the sequence, you're going to find one. You're going to find an ank that works. These subintervals go from rk to sk. That's my notation for the left and right endpoints of my subintervals. The rk's are increasing and they're bounded above by m. So, by the monotone convergence theorem, the rk's have to converge to a point r. Also, the sk's form a decreasing sequence bounded below by minus m. So the sk's have to also converge, let's say, to s. Recall that sk minus rk is the length of the kth subinterval, 2 to the 2 minus k times m, which goes to 0 as k goes to infinity. And now you compare limits on left and right, you get r equals s. So by the squeeze theorem, ank must also converge to the same limit. This gives us our subsequence, ank, which converges to a point, and that's our proof of the Bolzano-Weierstrass theorem.